Okay, we have problem number 7 is an ordinary differential equation, more precisely Newton's law of cooling. So I'm not going into the fluff here. We have this differential equation. T is the temperature of the material, Ta is the ambient temperature or room temperature, and this K is a cooling constant. First, we are asked to integrate both sides of this equation and show that the temperature difference is given by this expression. And for part B, we need to specify what is this constant C0 if we know that the initial value of temperature is 7 Celsius degrees and the temperature of the room is 20 Celsius degrees. Let's start with part A. We go back to the differential equation. We have dt over T, capital T minus 2Ta equals minus K times small t. Integrate both sides. Plus ln C0, which is a constant. Okay, the first integral is going to be ln t minus 2ta, because if you differentiate that, you get 1 over t minus 2ta, you get this guy here. That's going to be so it's dt here, it's not t, dt. It's going to be minus k times the integral of dt. The integral of k dt is just the integral of dt is just t plus ln c0. Okay, so the integral, this integral here, minus k dt, is going to be minus k integral of dt minus k times t. So we have ln t minus 2ta equals minus k times small t. T is time, capital T is the temperature, plus ln c0. Now I can bring this term to the other side. I will have ln t minus 2ta minus ln c0 equals minus k times t. That's going to be ln t minus 2ta over c0 by the properties of logarithm. When you have ln a minus ln b, that's going to be ln a over b as a fraction. Now to get rid of the ln's here, we use the exponential, so we use e ln, e to the power of ln t minus 2ta over c0 equals e to the minus k times t. The exponential with a natural logarithm will undo each other, and we have t minus 2ta over c0 equals e to the minus k times t. So t minus 2ta is going to be c0 times this guy will multiply this term here, c0 e minus k times t. And that's what I wanted to show. Okay, that's pretty much it. I've showed that T minus 2Ta, the difference of temperature, is a constant times e to the minus k times t. That's or I can write T as the temperature as a function of T minus 2Ta, which is the temperature of the room, equals C0 E minus K times T. Now for B we need to calculate C0 if we know that the initial temperature, so for T small, for time T equals 0, the initial temperature is 70 Celsius degrees and the temperature of the room is 20 Celsius degrees. Okay, let's go back into this equation and plug in T equals 0. We have T of 0 minus 2TA equals C0 times E minus K times 0. We have T of 0 minus 2TA equals E to the power of 0 is going to be just 1 times C naught is going to be C naught. T0 is 70 Celsius minus 2 times 20 Celsius so C0 is going to be 30. Okay, that's the final answer. C0 is going to be 30. And we can go back into this equation. T of T minus 2TA equals 30 times E to the minus K times T. And then we can obtain a formula for the temperature. Capital T is going to be 30 times E minus K times T plus 2TA. Okay, and that's the end of this part as well.